Hi everyone, welcome to June's Reagent community meeting. Today we have with us Adrian Filips, who is an independent researcher and analyst who's committed to multidisciplinary open source research projects that can help make a difference in today's world. His education background is in engineering, computers and molecular biology, and he currently works for the Environment and Climate Change Canada, but also heads up a group of bioenthusiasts at the Ottawa Bioscience Group. So as well as being an active member of these communities, he's also involved in organizations related to the promotion of open science, so like the Gathering for Open Science Hardware, so GOSH, Helpful Engineering, JOGO, the Global Community Biosummit, RECLO, and so on and so forth. Adrian believes in open, inclusive citizen science because currently the allocated resources are not sufficient to tackle the current challenges that we face in the world. And this very much chimes in with the RECLO ethos and what we're trying to do to build this open global collaboration for equitable access to biotechnology. So Adrian today is going to talk to us about a project that brings all these experiences together and share with us the development of this open and affordable robot for automating inoculations. So without much further ado, I'll pass it on to Adrian, and hopefully you'll be ready to tell us a bit more about your work.
Yes, hello everybody, I'm Adrian. Let me chase the slides somewhere in here. I'm sure all this. No. Okay. Will be open. Yeah, second. Slides. Come on. This one.
No worries, take your time. If you have any questions throughout Adrian's talk, feel free to also post it in chat. Myself and Sabelli will be monitoring that.
Okay. Challenge. Find where slideshow. Okay. Okay, I hope everybody can see the screen there, right?
We can see your presenting screen.
Yes.
With all the slides and stuff on the side. So I don't know if you need to switch screen or turn to click the slideshow button.
I did press the slideshow button actually.
Okay. It's funny, this literally just works just now, so I don't know what happened.
So now it works, right?
It's still showing all the slides, so not the presenting mode.
Okay, I'm gonna stop it and I'm gonna restart it again. Just bear with me.
No worries.
Okay, well, this one is supposed to work. Okay.
Still
yeah.
Perfect.
Is it okay now? Okay.
Yes, it's good.
Okay. So this is an inoculating robot, and we can go back into that. So what are the challenges in here? Well, the idea is to make the biology labs like community one be able to perform in low resource environment. And for that, obviously, as Jana was mentioning, we have to create low-cost devices, reagents, consumables, etc. So in most cases, the challenge is not necessarily we don't have to reinvent something, but it's reducing often by an order of magnitude while preserving functionality. So it's not necessarily to inventing, but just reducing costs. Okay, and the designs that I'm working on are made to be used. So, and they are used in my labs, and therefore they tend to be tested and they tend to be functional. Some of them are not. When you go on the internet, then you just download some design. So how can it came to be this one? So I had some success with other projects, but the lab robot was a little bit of a back burner because we were not ready for it because it's a higher level of difficulty. And one of the things that I noticed is that a project that takes months of effort in making is not realistic for a community lab. And for instance, let's take OpenTrons. It's open source, right? Well, it used to be open source, or it's partially open source. But I don't know any examples of somebody who built it besides OpenTrons itself. And the reason is very simple. It's like very large number of parts to acquire and long time to assemble and put it together. So the journey is kind of too long. So while I was being involved with this how to go almost anything course as a global TA, I noticed that there were students, the paying students, that were introduced to robotics, and they were using OpenTrons, and they were doing basically two types of projects. One was dilutions, and the other one was AGAR, which is basically an inoculation well, exercise. So, and when I looked at that, I thought that there was a solution that we could do that with far less far less expensive way. So, so the solution was using an off-the-shelf machine, and that is very cheap. It's like about $150, give and taken, of course. And not only that, but the fact that you can buy it off the shelf, it removes most of work in procuring parts and building it. Now, it obviously has some limitations compared to an industrial or robot. Or is sorry for that. So, for instance, the bed size. The bed size is much smaller than a normal one. Now, normally these robots have these slots where you put your labware, your plates and stuff like that. So, for instance, OpenTron has about 3 by 4, so we have like 12 slots. This one allows for like only four full slots. And if you want to put some smaller size slots, should be okay too. But now one solution to that is there are extension kits to extend the X-Y axis or Y axis. I think they're about $100. And so you can go with that. If you really want a big machine, you can buy a really big one. 6040, which is 600 millimeters by 400 millimeters. And that will be, I don't know, it's probably about $1,000. But anyway, if you just want to do an inoculation, and you can put like 196 or 2 or 396 well plates should be sufficient enough for the source of the inoculum. Okay. The other problem is the Z-axis, so how far you can lift it. This particular one has about 40 millimeters, which is not too much. Which means that if you put the labware, it kind of have to be at the same level, and you cannot put like very tall labware. Since you work with like very small quantities, it's not necessarily a problem. Then the other problem is that mine is much noisier than the lab robot, or at least I think it is noisier. Okay. There are some other differences there, though. So this is based on a CNC machine, and that has to be very robust. So it's much more robust than an OpenTrons. The head can carry much heavier burdens there. The precision is similar or better than OpenTrons. It has a smaller footprint. I'm not sure if that's well, for a small lab, that might be an advantage. Certainly is not an advantage in terms of how much complexity experiments you can do. And this one obviously doesn't come with an enclosure by default. Some people see that as a disadvantage. Some people see that as an advantage. My former PI was seeing having an enclosure is a big problem because he wasn't able to sterilize the robot. He wanted to use it under the hood there. Okay. And So if you look at comparison to other open source and kind of in the same space there, so there are many other robots. Most of them are coming out of the academic environment, and unfortunately, most of them are not maintained after publication. Uh, None that I saw used the unmodified existing hardware. Most of them will buy the specific pieces one by one, or take something like a 3D printer, dismantle it, and have to redo it, which is a fairly involving activity. But if you have patience and experience and expertise, and if you are interested in this, you can look at those for sure. Okay. As compared to commercial robots, of course, OpenTrons, for instance, I don't know why I keep saying OpenTron. It's OpenTron S. Has many modules and pipetting capabilities, but it's very expensive. The old model, it's which is OD2, it's $7,500. The new model it starts at $27,000, and even if somebody would donate it to me, just the import fee is going to be thousands of dollars. So the other thing is, because this was made for inoculation, it actually has much better resolution in that respect. Okay, so the first thing that you need, of course, you have to need some kind of holders for your petri dishes. So this is one of the modules that the design was used. This is how the box comes in. So the $150. It is actually it comes as a kit, so it needs a couple of hours to put it together. But basically, it has a bed, and it has this what's called the spindle, where it keeps the cutting tool there. So that I would have to remove the spindle, and I have to change the bed. And here is what's going to be in here. Oops. Don't see it. Okay, well, anyway, so this is the new bed. As you can see, it's still made out of plywood. There's a version of done in acrylic, which probably looks a little bit better. Initially, I thought that I should put some clamps in here because I usually clamp everything down, but it turns out that for this kind of application, you just don't need clamps. You just need very precise cutouts in here, pockets in here where you can basically place your lapware without too much of a play. Yeah, and you can see it in here with the one of the several modules, right? So the P2 dish holder, and in the back on it's a 96 well plate, and you can see actually that wire that comes from somewhere above. It's actually the tip of an inoculating loop. In this case, I did several experiments. The last ones, I cut the loop itself out, and I'll tell you why. But anyway, so if you look in here, it's like A, B, C, this is row H, and I believe this is 7. 1, 2, 3, 4, 5, 6. Okay, so it should be H. 8, 2, 4, 5. Yeah, so H6, like the source split. Okay, and so here is a little bit of a video. I'll have lots of videos. We'll see. So let's show it. Wow. So this has the loop actually. And if you look very carefully, when it actually touches the agar, it actually disperses the liquid without making a dent in the agar. You can achieve that if you want to. And you can hear the noise. It's a little bit less noisy in real life, but the way I capture the video was very close to the. You can see a little bit of the holder, that red holder, and the full inoculating loop. So it's just a regular inoculating loop where you can remove the. It's removable. You can replace it with any other one.
Adrian, are all
Yes.
your plates the same volume of media, agar, the same height?
No. So you're talking about the Petri dishes, or you're talking about
Yeah,
the
the Petri dishes, the agar plates.
No. Obviously, you cannot achieve that because when you pour the agar, you're not going to be able to control properly the height. So one of the operation is called calibration. So basically, you start the robot, you move the inoculating loop, you lower it down until it touches the or almost touches the surface of the agar, and you take that number and you will have to put it in your program in the software. It's very similar to the Opentron ones too. Yes.
So you can't detect the surface of the plate.
You would be able to detect the surface of some well, the surface of agar is very hard to detect because it's soft, right? You cannot film it properly. You cannot just push it and have kind of a mechanical switch in there. So for this one, yes, you have to do the you will have to measure it in a calibration method. That's exactly what the students who are doing with Opentrons or with the other robots do. Theoretically, well, so there are two parts to it. First of all, if theoretically you pour the same quantity, you might be able to get the plates at the same level. Now, the other thing I noticed, and I had to do it at one point was, so initially when you start dispersing, if you use a proper inoculating loop with a little loop at the end, every time when you touch the agar, all that liquid that's held by the superficial tension inside that loop will gonna be basically it's breaking and it goes on the plate there. And if you want to do like cute images and stuff like that, the fact that the colony grows, it's a little bit kind of a fluffy edges at the end. So if you want like very nice resolution, actually the best thing is to do like a little indent inside the agar, which means that the growth is going to be kind of in that place without extending it too big and becoming a little bit fluffier. And in that case, of course, you can, you can decide, okay, this plate, all plates are at this level, and you can stop the agar at the same height, and you would probably be able to skip the calibration. Does that answer your question?
Yep. I tend to pour my plates rather than pour my plates. I actually use a pipette. So for the large plates, I'd pipette about 30 to 35 mils of molten agar.
Okay, so in that case, you have a very good control of the height of the agar in the plate. So you would be able to do that. Another thing that you have to be though also very aware of is the inclination of the bed and even the place where you pour the stuff. So ideally, if you really want to get like perfect thing, you would pour it straight on the bed of the machine. And in that case, it's perfectly level there. But I've seen people pouring it in other places, or maybe not, or maybe the bed not being completely level. And I've seen that, one side of the image, it looks differently than the other side of the image because of the height there. Okay, so let's move to the next one. So I think you kind of saw most of the stuff in here. I'm going to move to the next one. Let's see. Oh, please. So, oh yes, you see the bend in that in the inoculating loop wire there? Well, I did that at the beginning thinking that it's going to be some resistance in it, thinking that it's going to be a little bit springy, but it turned out to be completely unnecessary. So that's not something that has to be done. Okay, let me see if I can which one. Okay, no, this one. Yeah, yeah. So this is a little bit of a different view there. Again, you see the head. You see how the drop is poured on it. So in here you can see a little bit better how what's the precision. So you see it goes straight into the middle of the well, no problem. As I said, the precision of this machine is like, fractions of millimeters. Okay, let me skip a little bit more. And okay, let's see this one. So in here, I think it's the same. Probably a different setting in here again. So this image will have probably about 300 dots. So the actual distance between these dots is sorry for that, is about 1 millimeter or something like that. The resolution is good. It's not the best one. Sorry for the background noise. Okay. Yeah. So again, different angles there. In this case, the program is fairly simple. You just take from the source, which is H, I don't know, 6 or 7, and you put it on the plate. Now, you have to prepare the plate with an array of points with coordinates X and Y, and the coordinates are based on the middle of the plate. So the origin is 0. So you're going to have minus and plus. Okay. Yeah, you can see how the line is coming together. Okay, let me see another one. Okay. And this is one that's a little bit different. In here, there's no tip, so that loop does not exist anymore. And this is a higher resolution. This is a maple leaf being built in here. And this is a 3-use GFP. Again, this is going to be a longer one. It's about 700 points. You're going to see it at the end of the presentation. And let me skip a little bit. Okay. So as you can see, the points are fairly well aligned there. I didn't realize it was so noisy. Right, and okay, and this is filmed under under UV light, so it looks a little bit cooler. So again, the source well and the maple leaf that's almost finalized. Yeah, that rattling that you can hear, there's a nut that goes on the main screw, and I figured out a way to stop that rattling after that. Okay, and I'm going to show you the program shortly and the result of this. I think I also capture some background noise while doing this. Okay. And this is the, sorry for the noise. So this is the result of the experiment. You can see the leaf in there. Actually, it looks even better in reality. And you can see, it's kind of funny, the edge colonies are doing a little bit better in terms of expansion there. And so this is probably, this is the 700 points there. This takes 2 hours or something like that to do, but you can leave it overnight, no problem with that. Another one after several days. It's kind of interesting because I think at one point, depending how fine the wire is for the inoculating loop, you actually end up not transferring the bacteria, but just the GFP in this case. So some of that will grow, some of that might not grow necessarily. Here you can see that some of that is growing a lot and some of them does not. Okay, and that's pretty much it. So the important thing is like there's no modification of the hardware by software. Okay, I'm also using another intermediate software developed by a lab at MIT that wanted to execute the same code on several robots. So practically, once you write the code in here, you will be able to execute it on Hamilton, on OpenTrons, and everything else. Of course, you still have to print your Petri dish holder. The one that I have on file is kind of the standard one, the 90mm ones, the plastic ones. Okay, and here's the sample code just to show you, give you some idea. Most of it is boilerplate, so this is where it starts, and we just say, look, the Petri is put in the first slot, okay, and go back to Scott's question, configure Z. Oh, no, this is not Z. Sorry for that. The source well in the 96 well plate, and we define the 96 well plate like this, and we create a Petri holder, and we assign it. We put a Petri dish in a Petri holder. Okay, and this is where the question for Scott was. So here I changed that value, and you can specify it in here. Change in plate variables. So this is 7.9 millimeters from the bed robot there. And in here you just load another file that happens to have the dot arrays. It's a text file, nothing complicated. And then the code itself is this for each of the points that we have in that array. We aspirate from a source well, which is at the H7, and you dispense into the coordinates that come with that point. And that's pretty much it. So once you do this code, actually it's a two-step process. So you do this code, and it will save it as a text file as a G code. And with that G code, you take it on a memory stick, or you connect it directly to the computer, and you execute it with the robot. And that's exactly what you saw in the demo there. Okay, and see how to do this part. And let's see. Yeah, so the workflow I was telling you, so modify the sample code, you generate a .g code file with robot instructions. You take that file and you load in another program called Candle in this case. You have to calibrate the machine, so you set it up where X is 0 and Y is 0, and with that of the agar, which is calibrated instance from the inoculating to agar, and you do the inoculate. So now there's also some potential enhancements I thought about, but I'm not sure if I'm going to do them at this time. It is possible to self-sterilize the inoculating loop by running an electric current. So that way you can programmatically say, kind of almost like a change tip kind of situation there. So that would not be extremely complicated, but I would have to modify the software on the machine. And it is possible to add pipette support. There are lots of OS pipette designs to be added, that could be added. Yeah, so the full documentation is in here, and it's a real documentation. It's not like halfway. All the models that are put in there is not just a PDF that you can produce it but not modify it. It's full files that you can take and modify and adapt if you necessarily want to. And includes also the labware and the holder for the inoculating loop. It will accommodate the inoculating loops of different sizes. The models are also parameterized, so you can change the parameter if you really need something else. That's basically it. And if anybody has any questions.
Great. Thank you, Adrian, for giving us that rundown of your robot, and thank you for persevering, because I know you said you weren't feeling very well today. I think I'm gonna pass on to Sibeli, who will be handling the Q&As for the session. I think we saw some in chat already.
Yes, thank you, and thank you so much for sharing the videos. It's really exciting. And yeah, thank you so much for the awesome work. And yeah, so we had some interaction on the chat. Everyone, again, please feel free to either raise your hands on Zoom to ask your questions or send them on the chat. So I think one of the first ones we got is asking if the robots are Cartesian.
Yes, this is a Cartesian robot. It's there are two types of robots. There's the Delta ones and Cartesian ones. This is the one that's basically ubiquitous on the market there. Yeah, so basically it's a machine that moves in the head anywhere you want. You say go to X equals 5, Y equals 20, Z equals something else, and it will do that. And you can even set if you wanted to use metric or imperial. Yeah.
Great. And then, well, Scott sent us the links for the GitHub repositories, and now Yankee just shared some of the videos that we saw today and some other really nice videos. So make sure, everyone, that you check our chat. And yeah, so we also have some questions. So Scott asked a bit about the agar plate, so that they can vary, and how do you exactly can calibrate how high they are for the robot to know and not go too deep or not actually work on the process.
Yeah, so the calibration is fairly standard and it's done with everything, including laser cutter and stuff like that. So basically you have a program that you have an interface and you put the robot on the table, and if you press arrow down, the head is gonna go down. If you press arrow up, the head is gonna go up. And you press a button that you press the arrow up until you and left and right until you bring the head or the inoculating loop over the agar plate, and then you press it down, and you look and you see exactly when the tip kind of touches the agar plate, and then you look on the screen and you see exactly what the Z is at that time, and you write it down. So that's the height of the agar plate. It's the same process that you use for all the CNC machines, sometimes for laser cutters, or actually for laser cutters, and sometimes for 3D printers. 3D printers have home limits, so it can auto home. This machine, being cheap, doesn't have auto homing, but it has auto homing capability. So the board, it can support auto homing. The software can support auto homing, but you do have to buy the little switches. I don't know, it's about probably about $30 worth of it, or $5 a piece. And you can separately. I didn't do that. It's necessarily to do that. I understand that OpenTrans doesn't do that either. Doesn't have auto homing, but I might be wrong. For such an expensive machine, it should have some kind of auto homing, but it might involve just banging the machine to the left side, and then the machine will say, okay, that's the limit. I cannot go further. This must be zero, x equals 0 or something. Actually, Scott has an OpenTrans. He would be able to.
Yeah, the OT2 does home.
Okay. So
Yeah.
So that's the home. In this case, what I do, I go with the arrows until the one corner on the bed, and then I press a button in the software that says, okay, this is where x equals 0 and y equals 0. It's not so complicated. It's fairly simple, and I get perfect precision into putting the inoculating loop straight in the middle of any well there. The only problem is sometimes the inoculating loop is not like perfectly straight. So you kind of have to look a little bit careful to understand exactly what it is. But yeah, that's not a major item.
So Adrian, so this is nice if you want to draw art. Are you working towards trying to say, for example, replicate, like if you have deep wells, a deep well plate where you've got the 96 wells, and you're going from one well of one plate into a clean well, you'd have to sterilize before. So have you thought about different ways of, you've mentioned about using electricity to sterilize the loop, but I wonder about putting it into maybe a series of cleaning steps in between where you're sanitizing the loop.
Yeah, in principle, that can be doable. As a matter of fact, when I did this one, I did some images that were using several source things, and actually I flamed the loop straight on the machine, because I have a small like flambe kind of flamer there, and it works out. I think, well, you probably can do that chemically, I guess. I still think that the burning iron thing would work quite well in terms of sterilizing, because there are also like devices to sterilize electrically the loop. And that would be nice because you wouldn't have to, with the pipettes, you have to throw away the tips. Yeah, go ahead.
So your loop is nichrome wire?
As a matter of fact, right now the loops, well, I have some loops that are platinum and some that are nichrome wire. But yes, I would have to redesign that loop in such a way that you have two wires, and then at the end you'll be just a nichrome wire, and that would be very nice because then you can sterilize it whenever. It's very cheap, it's very fast. It's probably several seconds, and it will work quite well, and it would not be necessary. At this point, I'm not using the spindle signal, because once you take the spindle out, I'm not using it. So I can use that one to basically run the sterilization. And it will have enough current, it will have enough power on the board itself. So you wouldn't have to go and buy other things. So you still keep everything within $200. And then you can sterilize it forever. Now the other thing is like I don't know. I'm not sure if you do that, you're gonna build something on the tip. Probably not, but that's possible. And again, I also mentioned it is possible. The head is very strong. You can put a big pipette in there. You can probably put a commercial pipette, but for that I would have to change the software on the motherboard to to be able to do the heat ejection and the calibrate the change the quantity
Yeah.
for the pipe that we
Yeah, great. And well, talking about also other applications, we have a question from Joseph. I don't know if you want to maybe open your microphone and ask. I could also read it.
Can you hear me?
Yes.
Yes. I wanted to ask if there is some problem that I have some in some occasions that I need to pick a single colony that is uh, massively surrounded by other colonies, but this colony is expressed. Can this robot be used with like a surgical precision robot inoculation robot to take only from this single colony and try to inoculate an agar plate?
Well, obviously, right now it cannot do that. Well, you can if you want to do it manually. If you turn on that program candle that lets you go left and right and left and right, you can position it exactly over the colony that you want to do, and then you just press Z down and then Z up, and you would at least touch that colony there. So you could manually do that, and normally that I'm not sure. You can. Again, the head is pretty. I can put many things on that head there. I could put a video camera that will allow you kind of programmatically uh, identify a colony and do the scooping directly there. The precision is very good. It's like under 0.001 millimeters, so let's say 0.001 millimeters. So as long as your tip is not too big, the loop is not too big, or you cut the loop as I did, so I get like a better smaller dots, you will probably be able to achieve that. It also depends on your application. If you want to do it once in a blue moon, or if you want to do it, 10,000 times in some kind of a directed evolution experiment. And we can look at that in terms of time investment.
Right. Wow. Already a lot of ideas to expand on the work. And yeah, do we have any other questions from our audience? Adrian, of course, is already on our Recon forum, so you can definitely also continue talking with him. We have both the thread from the community call today, but also we can always start a thread talking about the inoculating robot and other ideas around open hardware. Of course, with our very close to us community with Kosh that we have worked with before. And yeah, do we have any other questions?
Actually, maybe one thing I wanted to mention is like the modules, like the plate holder and I think I might have some more. They're actually independent of this. You can take them and you can use them on OpenTrons or probably on Hamilton or something like that. Because they were made to be interchangeable. And if you need some other, if you use smaller plates or something like that, just contact me and I'll show you how to. They're parameterized, so basically there's a file that holds the diameter of the plate. So if we change that one, we can create 2.60 millimeter plates and stuff like that.
Great. Uh, Okay, I actually have some other questions then from Yankee and I that we had separated here. Yeah, so one of the questions we had is, so you recently finished the work with the robot, and like, how is it been? Like, do you already have other users still on your lab? Maybe we have some partnerships happening here with people interested in also testing it out.
Well, at this point, I was at one point I was hoping to get an open trans through like some other, well, to another course there, and that never happened. And I realized that some of the import fees were very would be like, $5,000 to $10,000 just for the, even if I get that for free. So the reason was I used it for some of the course students to execute remotely and create this agar art. Um, in the future, I'm looking, but it's not going to be the immediate future. I'm thinking maybe I can try some directed evolution, but for that I might have to add the pipetting capabilities or some other capabilities that we don't have right now. Oh yeah, so I've seen people doing agar using like the pipette tips, but the result is not very good because the pipette tips are not very and they are not very precise in terms of dispersing liquid in one very small place there. So they don't necessarily go so well. Yeah, in terms of partnerships, I don't know, like, it's open. I can help anybody that wants to build one. Uh, it's not even worthwhile me sending something like this to somebody because shipping would probably gonna be as expensive as I mean, yes, we can do that, but it's probably easier for somebody to just buy it and I can probably print some of the parts. It's not very complicated. I mean, you bring the pipette holder, another piece for the loop holder, and you have to build to cut the bed to with the slots, and that, I mean, you can 3D print that one if you are into self-punishment, because it might take 2 days, but and I can make a model if you really want to print it. But you can probably cut it on a laser printer in like 15 minutes, 10 minutes, which is a little bit easier. So laser cut is so much easier. And yeah, so I'm open if anybody is interested in replicating and try it, and either for research or for teaching purposes or for understanding about robotics in biology or anything else.
So I posted in the chat a paper on the evolver system, which is being used for directed evolution. So you might want to have a peek at that. And there are a bunch of papers that come out. There's a forum of a lot of people working on it.
Thanks for
Yeah,
sharing that, Scott. That was something that I was quite interested in as well. See what kind of directed evolution work you can do, because so far it looks like it's a lot of like bio artwork, but this is a nice outlet for research. Sorry, I interrupted you, Adrian.
Oh yeah, no problem. I do have this great filing system where it's a text file where I type the links and stuff like that, and I have that one in my on my list. Thank you so much, Scott, there, because I was starting to collect some ideas about the directed evolution processes that can be done. I was looking at the Professor Liu's directed evolution and some other ones, and it would be yeah, as I said, I would be very interested to do that because that's where the power of robotics, especially, except for the teaching and except for the fact that actually you can teach somebody from somewhere else that, just do the program and I'm going to execute it in here and you can see the video. So even if you don't have a lab, that's one I think valuable use case there. But the other very valuable use case that I can see is also directed evolution where you can do like this thing for weeks and not getting bored and stuff like that. The other thing that I might think that might be useful for a clone might be, for instance, creating sending kits on paper or on plastic, because you can precisely position things into small places, and you can make kits day and night without having to, you know, to check yourself into a psychiatric facility there. So that might be also a good thing, and that's kind of where I think that maybe that self cleaning mechanism of the pit might work. I did check the quantity dispersed with the simple wire. It's um, quite stable. So you know, once you actually you wet the tip, every time if you dip it at the same level, you get about the same quantity, and it can be very small. So it's like could be under 1 microliter, which might be also interesting if you want to like distribution kits there. So these are the kind of some of the use cases that I thought that might be useful besides, you know, just doing the impact.
That is an interesting idea, and it's actually you're right. One of my poor colleagues did do a lot of manual spotting of DNA onto, well, this was DNA, not strains, but onto paper. But it's something that probably we could look into. Try that as a distribution method. The only reason why we stepped away from spotting DNA, in this case DNA, onto paper, was that the recovery and then subsequent transformation wasn't as high as if they got it in 96 hot plates. But we're not quite at the stage where we're well sending strains specifically. But this could be something we revisit in the future. So thank you for giving us that suggestion, Adrian. Yeah, I did have a quick question in terms of the software side of things, because I could see in your script that you were quite diligent in actually putting comments of what to edit here and there. But for folks who aren't as familiar with this, would you consider putting it, making the script into like a Jupyter notebook or Colab so that they could literally just run a cell and input numbers?
Yeah, obviously, if there's interest, I can do that. Again, I'm piggybacking on this other script done by the guy in MIT, which kind of makes it, once you write it in this script, you can decide, okay, I deploy this on OpenTrons on I think it supports about 4 or 5 robotic systems there. Yeah, if there's need and somebody wants, I can probably try to do the Jupyter notebooks. I usually don't use those personally because when you're a developer, you usually do it the other way, but I can do that, no question about it. The scripting is fairly simple. I mean, you just once you do the confirmation, you say like put this one in slot, blah blah blah. Put this one in slot, blah blah blah. The 96 well addressing is fairly simple. You say put it in H7, whatever this case was. So it's not extremely complicated. The most complicated part is actually the setup of the development environment, which can be which is can be frustrating in some cases too.
So yeah, well, we are about the time of the sessions. Thank you so much for sharing. Thank you so much for answering the questions. As I said, and as Yankee shared, we have the topic for the session today on our forum. So everyone is invited to continue interacting there, especially you, Adrian. Thank you so much for joining us and starting this conversation also on our forum. Thank you so much for the session today.
Thanks, everyone.
Yeah.
Thanks,
Thanks
everybody.
again, Adrian. Thanks, everyone. And see you next month.
Bye-bye.
Take care. Bye.